Never trust an atom. They make up everything. You and I exist on a certain scale. We exist on what we sometimes refer to as the macroscopic scale. And the macroscopic scale is essentially the stuff that you can see. So planes and trains and automobiles and cats and dogs are all things that exist on this macroscopic scale. And there's no exact definition for the size range that the macroscopic scale encompasses, but a good general rule is that things are macroscopic down to about 1/10 of a millimeter. So if you think about your typical kind of centimeter ruler, and then of course, between any two whole numbers, you're dealing with a centimeter. And then if you go and look at these tiny little gradations in between, those are what we refer to as millimeters. And if you divide that little interval uh, up into 10 sections, then you'd be looking at 1/10 of a millimeter. And that's about the lower end of the macroscopic scale. And if things get much smaller than that, that's about where you lose the ability to see them. So you really can't, with your naked eye, you really can't see things unless they're at least about 1/10 of a millimeter large. Now, below the macroscopic scale, we have the microscopic scale. And the microscopic scale is the things that you can see with a microscope. And this is a problem because we're defining the size relative to our technology. But as microscopes have gotten better, we've pushed that down to the point that things can be on the microscopic scale down to about 0.001 millimeters, about 1/1000th of a millimeter. The reason I'm bringing this up is because we're at the beginning of a chemistry course, and we are facing a bit of a problem. Because chemistry, the study of matter, is going to require us to start looking at atoms. Atoms are sort of the fundamental building block for matter. And the problem that we run into is that when we start trying to deal with matter, we're going to have to work on the atomic scale. And the atomic scale gets down to about 0.6 zeros and a 1 millimeters. And at this point, millimeters is not even really a very good unit anymore. We would switch over and use something like nanometers. But I'm keeping it there just to point out the problem here, that we are going to be dealing with atoms, and that the size of atoms is so small that it is tiny even compared to the microscopic. You and I have all these intuitions about how the macroscopic universe behaves that come from our everyday life. They're built into your daily experience. In some ways, they're even built into the psychology of the human brain. We're pretty good at intuitively understanding the macroscopic scale. And we're okay at the microscopic scale because it's only a few orders of magnitude smaller than what we're used to. Our intuitions are terrible when it comes down to the atomic scale. We're going to run into a lot of situations where things maybe don't behave the way that we would want them to in the macroscopic world. So we're going to start today by talking about the idea of particles. And this is really our introduction to what we call the particle model. I want to start our discussion of the particle model by talking about this particular example of matter. So we're looking at matter here. Matter is anything that just takes up space and has mass. And you can probably tell just looking at this image that I'm dealing with some sort of metal here. So I'll ruin the suspense a little bit and tell you that what you're looking at here is a chunk of metallic iron. It's a solid at room temperature. It has this kind of gray silver color to it. And those are macroscopic properties. But what if you could zoom down to the atomic scale? And what if you could look at what it's made out of at that tiniest of scales? If you could zoom down to that atomic scale, what you would find is that this is made of atoms, and it's made of iron atoms. The abbreviation for iron is Fe. Don't worry about that too much for right now, but I'm going to use that shorthand. But what you would find is that there's a particle of iron, and then next door there is another particle of iron, and then next door down here another particle of iron. And there are these individual iron atoms that are just simply adjacent to each other. Now, that is one example of a sample of matter. This is an example of what we're going to call an element. And the reason I'm calling it an element is because there's only one type of atom. It's just iron atoms. There's no atoms of any other type. There are only a limited number of elements. We have been able to identify the elements and to put them on a nice convenient table. I'm sure you've seen this before. This is the periodic table. And the periodic table lists every kind of atom that there is. All atoms are made of protons and neutrons and electrons, and there's only so many ways you can put them together, so there's only so many atoms, so many elements that you can make. And if you look right over here, you'll notice that iron is in fact listed on the periodic table. Anything that appears on the periodic table is an element. Anything that is an element will appear on the periodic table. So it's a nice correspondence there. The easiest way to know if something is an element is to pull out your periodic table and look for it. Now let's take a look at a different sample of matter. We're going to take a look at water. I like water as an example because a lot of people come into chemistry with a mistaken assumption that water is an element, and it's actually not going to turn out to be an element. If you look at the periodic table, you will not find water. And the reason is because if you zoom in and if you look at water at an atomic scale, what you're going to find is that water is made of particles that consist of one oxygen atom and two hydrogen atoms. And you probably know this is where we get the shorthand for water, H2O, from. But the important concept right now is that one particle of water actually consists of three atoms. One atom is oxygen, that's an element. The other two atoms are hydrogen, that's another element. And what we've done here is combine them, we've attached them together. We call it chemical bonding. We're going to deal with it at a later time, but the important thing is that the oxygen and the hydrogens are semi-permanently attached to each other. At least right now in this context, they're permanently attached to each other. So what is this? Well, this sample of water, it's not an element. We have a different word for it. We would call it a compound. And the reason that it's a compound is because there's two or more elements. And they're bonded together. And that's what's making up the particles. All right, sometimes you'll hear this particle referred to as a molecule. It's another word that we'll use more as time goes by, but the important thing is that this is not an element, it's a compound. Now, of course, this glass of water is not made of one or two of these. It's made of an almost inconceivable number of these. So there's one water molecule, and then next door there's another water molecule, and then next door there's another water molecule, and there's an innumerable number of them in there. But if we go and start looking at the water at an atomic level, we start looking at it at a particle level, you've got a particle of H2O, you've got another particle of H2O, you've got another particle of H2O, and that gives us our compound. Okay, so let's take a look at another example of matter. And what I want to look at here is the just atmospheric air that we're all breathing right now. So the air that you're breathing is, of course, like everything else, it's made of matter, it's made of atoms. But air is a little bit different because it is actually a mixture. What I mean by a mixture is that there are different types of particles that can be found in there. So the air that you're breathing in right now, for example, it contains a lot of nitrogen, N2. So nitrogen consists, N2 is a nitrogen atom bonded to another nitrogen atom. But that's not the only thing in the air you're breathing. It's about 70%, but also in the air that you're breathing is O2. And O2, of course, consists of one oxygen atom attached to another oxygen atom. Additionally, in the air that you're breathing now, there's some water vapor. Water's in a gaseous form, but it's the same particles that it was before. So you've got an oxygen atom, which is attached to a hydrogen atom, which is attached to another hydrogen atom. And then another example, one of the things that's in the air you're breathing right now is carbon dioxide. And carbon dioxide consists of a carbon atom, which is attached to an oxygen atom, and then it's attached also to the second oxygen atom. So when you look at air, we have an array of different particles going on here. So we've got nitrogen up here. This would actually be an element because there's only one type of atom in there. Even though there's two of them bonded together, it's still only nitrogen, so it's an element. And then the O2 would also be an element. There's two of them bonded together. Certain elements do that. We'll deal with that later on. The water down here, well, this is a compound because we have two or more elements, and they're all bonded together to make the single particle. And then the carbon dioxide would also be a compound. But then when we mix them all together, what we get is what we call a mixture. And mixture, that word is meant to imply that there's different particles in there, that there's different substances. It's not really, if you could zoom in on the air, if you could get down to that atomic scale, not all the particles that make up air are the same. Some of them are nitrogen gas, some of them are oxygen gas, some of them are water, some of them are CO2. There's some other stuff in there too that we're ignoring. And we do tend to refer to air and other mixtures like this as homogeneous mixtures. And all that we mean by homogeneous mixtures is that these particles are pretty much mixed evenly, at least as far as we can tell visibly. For our last example today, I've got this glass of Coca-Cola with ice in it. And I want to use this as an example. This is a heterogeneous mixture. So first of all, key on the word mixture first. It's made of different things. So what's going on here? Well, if we sample the cola itself, we're going to find that there's a lot of water. So we certainly have water molecules. That's most of it. There's a lot of sugar molecules in there also. So there's probably more than one sugar, but the most common one is sucrose, C212, H22O11. So that's also just in what you think of as the cola, the soda itself. But then if you look closely at this, you'll notice a few other things. You're going to notice these bubbles, right? And those bubbles, that's the carbonation. In other words, it's the CO2 that is in there. And you'll also notice that we added some ice to this. So we've got these ice cubes. And the ice cubes, of course, are just frozen water. So you have more H2O over there. So the different particles that are in here, the different compounds and elements that make this up, are not evenly mixed. And that's visibly obvious. So we refer to it as a heterogeneous mixture. Right? Heterogeneous just means it's not the same throughout. There are differences depending on where you look in the sample. All right, so the last thing I want to look at then with you is this chart. This chart is meant to help you categorize matter by thinking about it in terms of particles. So if we take any sample of matter, it could be iron, it could be air, it could be cola in a glass, it could be whatever you want it to be. But if we take any sample of matter, the first important distinction we should be able to draw is that it's either a pure substance or it's a mixture. It's a pure substance if all the particles that make it up are the same. So when we kind of fast forward down here, you'll notice there's one type of particle here, there's one type of particle there. It's a mixture if there's multiple types of particles, there's different substances in there. So if we assume for a minute that we're talking about a pure substances are either elements or they're compounds. How do you know? You have to look at the atoms that make it up. If it's an element, it's going to be like our iron sample, where every atom is an iron atom. Or it might be like oxygen gas, where every atom is an oxygen atom. Or it might be calcium, where every atom is calcium. But it's going to be one element, right? You can always go and look at the periodic table if you're not sure if something's an element. When you get to a compound, you're dealing with more than one element involved. So something like H2O, where there's hydrogen and oxygen, or something like CO2, where there's carbon and oxygen. That's actually what this diagram is meant to be. So those gray spheres are meant to be the carbons, and then the red ones are the oxygens. Now, on the other side of this chart, we have mixtures. So if something is a mixture, it's either a homogeneous mixture or a heterogeneous mixture. With a homogeneous mixture, the particles are mixed more or less evenly, and visibly speaking, you can't really see distinctly different parts. Right? Again, think about the air that you breathe right now. It's not obvious that there's multiple substances in there unless you really get down to an atomic scale. Right? So air was a good example that we used here. A heterogeneous mixture, things are grouped up. And you get that impression, I think, from this diagram. I really like this diagram because we've clearly got some particle down here. We've got some other particle up here. This is a compound, that's a compound. There's two different compounds in here, but they're clearly not mixing well. Right? There's clearly a separation here. And even though we are looking at this at the atomic scale, I'm going to bet that if you could scale that up and if you could see this matter at a macroscopic scale, you can probably see that there are two different substances going on in there. You probably see some sort of layering where this substance is found in one place and this substance is found in a different place. It's probably visibly obvious to your eye that these are not well mixed. And that's why we have this little note up here, right? The key thing with a heterogeneous mixture is it has distinctly visible parts, as opposed to a homogeneous mixture where it seems to be evenly mixed throughout.